Welcome back to Advent of Code 2019, day 13, the halfway mark. Things will just get harder and harder. Let's have a look then. Care package. Looks like a short one. Well, short description. It uses ink code. Of course it does. Doesn't seem to change the ink code though. Right. Just put the kettle on. All right. As you ponder the solitude of space and the ever-increasing 3-hour round trip for messages between you and Earth, you notice that the space mail indicator light is blinking. To help keep you sane, the elves have sent you a care package. It's a new game for the ship's arcade cabinet. Wikipedia for arcade cabinets. Cool. Unfortunately, the arcade is all the way on the other end of the ship. Surely it won't be hard to build your own. The care package even comes with schematics. All the way on the other end of the ship, okay. The arcade cabinet runs intercode software like the game the elves sent. Right. It has a primitive screen capable of drawing square tiles on a grid. The software draws tiles to the screen with output instructions. Every 3 output instructions specify the X position, Y position, and tile ID. Tile ID is interpreted as follows. 0 is an empty tile. 1 is a wall, 2 is a block, 3 is a horizontal paddle, 4 is a ball. Okay. Start the game. How many block tiles are on the screen when the game exits? Alright. So it's not actually a game it's the ball isn't moving or anything, right? This is pretty easy. We just run the program. So last time it was 11 when we ran the program, so we can just do this. Okay. So that's our program. We supply an input. I see. So there's no input to the program. We just run it. Like, what did we do before? If we don't get any output out, we break. Okay. All right then. So let me just get my copy then. So I think it's just a basic, what we just do a while loop, and then as soon as we see a none, we break. So, uh, right. While true, let's take a look at encode as well. So if I keep calling get output, it will give us none if it's ended. Okay, so the three values it gives us in a chunk are X, Y, and ID. X, Y, tile, ID equals. Or just, I don't know, just do X equals int code dot get output, Y equals int code dot get output, tile ID equals that. Here, if X is none, break. All right, so we get the X, the Y, and the tile ID. And now we only care about how many blocks there are, but they could be overwritten. So tiles equals just default dict int. So everything's 0 by default, it's empty. And basically, whenever we get this instruction, tiles X, Y equals tile ID. And then it's part one. We just count how many twos. So some might be overwritten, but we just It's just going to be tiles dot values dot count 2. No, not count. List 2. So it just counts the number of 2s. And of course we've got to print it. $301. Nice easy problem to begin with. Part 2. The game didn't run because you didn't put in any quarters. Unfortunately, you did not bring any quarters. Memory address 0 represents the number of quarters that have been inserted. Set it to 2 to play for free. Okay. The arcade cabinet has a joystick that can move left and right. The software reads the position of the joystick with input instructions. If the joystick is in the neutral position, provide 0. If it's left, -1. What the heck? Okay. This would be cool to visualize. I can't be bothered to do that. Someone's probably already done that. But I'm guessing it actually plays out like a proper game. So you can watch the ball bouncing back and forth. Alright, so... Doesn't look hard. Just run it and that's it. Okay, part 2. So we need to modify the program. Program 0 equals 2. Let's step up credits. We run a new ink code. Wait. Wait, I'm not sure that I understand about this joystick business. So this runs. It's still going to run, but it's going to hang because we need to provide an input. Okay. Joystick. Alright. I'm guessing they're hinting that we're supposed to be playing the game. So... So wherever the ball is, we want to move the joystick towards that. Alright, well, we're going to have to override the inner workings of the int code. So I would say every time the ball moves, or the joystick moves, oh man, the paddle moves, then we want to update whatever is sitting in the input. So the queue just has to be cleared, and then we put something on. We only have one thing on the queue because of the way we've done the queue system. It's a bit weird, but we can do it this way. Or we can change. We can modify the module. So instead of putting an input, we can provide fixed inputs. This is one value which stays permanently every time input is called until we change what that value is. Self dot fixed input is B. So initially it's none. Alright, so whenever we get an input, we ignore whatever is on the queue, basically. So where do we get what's on the queue? Here. So input value equals self dot fixed input if self dot fixed input is not none, else self dot q dot get. All right, so if we have a fixed input, always provide that. Otherwise, fetch from the queue. All right. Okay, so if we use that, then I think we can, so we change that to 2 credits, run the program, set, we're going to set it to 0, so just keep the paddle steady for now. So there's going to be a unique ball and a unique paddle, right? the moment we write those, then they'll be updated. So, okay, so X, blah, 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 Y. Okay, so we update the tiles. If the tile was a paddle, it's 3. If tile ID is 3, then we now found the paddle. Just update that because we need to keep track of that. And if tile ID is ball, which is 4, ball equals X, Y. Alright, so we update those. Now I would say if tile ID is either of those, we want to update where we're moving the joystick. So if all is not none and paddle is not none, right? Because otherwise we haven't actually drawn them yet. We want to say if ball, the X value is strictly less than paddle X value, then we want to update the fixed input to be -1. We move the paddle to the left. So that's how you play. Elif is greater than paddle 0. Otherwise, just provide 0. Alright, so then we just try to follow the ball, I guess. What else? So that handles the joystick. There's the segment display. So the score. If XY is -1, 0. If XY is -1, 0, then then we get the update the score. Score equals tile. This can be here. It's probably 0 to begin with. Score equals tile ID. Skip all the rest of this. Okay, so this is as before. Print score, but wait. Beat the game by breaking all the blocks. What is your score after the last block is broken? Ah. Because this will probably go on forever because we keep breaking blocks. 14096. Well, is that the only way to get points? I don't know, but let's be completely safe and say if so after all this is done, if tiles dot values all t is not equal to, so none of them are blocks. I want to break out. And we get 0. Oh, because it's the beginning of the game. If I reckon you only get points for breaking the blocks, so we can just run the program like this. 14096. Correct. Well, that was a nice problem. We actually played a game. We played a video game via a program. Except we didn't really see it visually. We could, but it'll take a bit of work. Should we do it? Let's see. How would we do it? What are the coordinates we're actually dealing with here? Let's say define display. Height equals max of P1 for P in tiles. Width equals max of P0 P in tiles. Mat equals just an empty space for so that's the matrix, and then just put all the tiles in. So for X, Y, P in tiles.items. Does this actually work like this? Unpacking? That's fine, probably. So should we say if T is, this should be an empty space. All right, if T is 1, it'll be a wall. Should we say that's just a cross? LFT is... We don't need to do if-else's like this. We can just do a map like this. So it's going to be 0, empty space, 1. I mean, we can go even simpler than this. Just do this. Let's do a string. So it's going to be space for the empties, then cross for wall, block. We say dot. Oh, something with a bit of volume. Star. Horizontal paddle. Underscore. Ball. O. Or big O. O. Okay. So we don't need to do one huge okay, mat y x equals cars t. So that's display. So let's say every time the ball moves, or row in at print, join it up, and then print an empty line. And then if the ball moves, just display. Alright, I don't know how many frames we're going to get here. List index out of range, mat, y. Okay, what was... Height is the y values. Is this right? Should I do dot keys? Should we add 1 because it could be... Oh, right, because we're including the zeros, I guess. Yeah. Of course, yeah. Oh, man. Can we... See, the problem is it outputs like this. Is there a way we can make this into an animation? We can try and have a look at this, but... So we start off with just... Oh, this is towards the end. Ah, so it's deleting and adding the ball. I didn't think about that. Well, I guess that's fine, because if we're removing... If we're removing the tile, we shouldn't actually be moving the... it's fine, because they get added back in the next turn. Yeah, we can see it's actually bouncing off the paddle. So we don't have a say in where the ball goes, unless we lose a life. You can sort of see it moving. Oh, it actually ends for us. We don't have to manually terminate when there's no more blocks. What a cool concept for a problem. That was pretty clever. Okay, so that's day 13. Wonder how people did with that. Because it's kind of on the easy side, 8 minutes. That's a bit high, actually. Easy side if you've got a working int code. That's the big if. Yeah, people found it a bit hard. I guess it's a lot to think about, but pretty good problem. Okay. This is another planet. Number 14. Space stoichiometry. Uh-oh. Oh. Oh, it's some sort of scheduling problem. Okay, I'm good with these. Oh. Browser up. As you approach the rings of Saturn, your ship's low fuel indicator turns on. There isn't any fuel here, but the rings have plenty of raw material. Perhaps your ship's interstellar refinery union brand nanofactory can turn these raw materials into fuel. You ask the nanofactory to produce a list of reactions it can perform that are relevant to this process. Every reaction turns some quantities of specific input chemicals into some quantity of an output chemical. Almost every chemical is produced by exactly one reaction. The only exception, ore, is the raw material input to the entire process and is not produced by a reaction. You just need to know how much ore you'll need to collect before you can produce 1 unit of fuel. Each reaction gives specific quantities for its inputs and outputs, and output. Reactions cannot be partially run, so only whole integer multiples of these quantities can be used. It's okay to have leftover chemicals when you're done though. For example, the reaction 1A, 2B, 3C to 2D means that 2 units of chemical D can be produced by consuming exactly 1A, 2B, and 3C. Hello, Animo. You just need to know how much ore you'll need to collect before you can produce 1 unit of fuel. Each reaction gives... Oh no, we read that bit. Okay. Suppose your nanofactory produces the following list of reactions. 10 ore to 10A, 1 ore to 1B. Okay. It's kind of like a linear algebra problem in a way. Alright, I get the examples. Given the list of reactions in your puzzle input, what is the minimum amount of ore required to produce exactly 1 fuel? Minimum amount of ore. I was thinking some sort of breadth first search, but that would just... So if we do a depth first search where each state is like what is tuple of quantities we have, and from one state to another is we apply one of the recipes, then then that will basically tell us the Boolean, can we get fuel or not? And if we're trying to find the minimum amount of ore, basically we could start from 0 ore, go to 1 ore, then 2 ore, then 3 ore, and so on until we get the amount of ore required for 1 fuel. Or better than that, we could use binary search, but might not even be necessary. Oh man, there's a lot of options here. So where's fuel? Here. I'm guessing some of these recipes lead to dead ends, like useless materials, so that'll stop us trying to just do every recipe whenever we have the option. So this needs DBVD, CINMW, ZTCM, RNS. I think we should trim this. Like, I'm guessing some of these recipes are useless. Like, I don't know, like NRBGS produces that and that. Produces these and these. Like, I feel like some of them might lead to things we don't need. I don't know. Okay, I mean, I know how to program this. I'm just worried it's just going to take too long. Okay, well, whatever. We'll try the breadth first search approach. Because I don't see a fast way of doing it. You could do some pruning. Alright. So for each line, what are we going to do with this? First, we just need to know all the different variables, and then create a sort of map. Alright, let's think. Right, I think we need to create a class called like ingredients or something, which is basically represents a vector of ingredients. And we also need to store recipes. Let's just... Alright, let's do some splitting here. Left, right equals line.strip.split on this symbol. Left equals left.split comma space. So we'll just get these tokens on one on the left and one on the right. You only ever get one thing on the right, which is useful, I guess. Might help simplify things, but you only get one thing on the right. Okay. Right, so right will be a string on the right. Left will be a list of strings. So for now, just say recipe equals just the left and the right. And we'll keep all the recipes here because we have to process them further. Okay. Alright, we need to figure out this class. It's going to be class, let's call it ingredients class. Is that what we want to call it? Yeah. So this is just going to represent a vector, essentially, but it's going to be stored as a dictionary. So it's like, so should we make this a data class? I don't think there's any reason in this case. So we're going to provide this a list of pairs. Each pair has an ingredient and its amount. Like amount ingredient. So self dot, let's call it I don't know, amounts equals default dict int. So it starts off as 0 for all ingredients. Now for name, no, it's going to be amount name in ingredients. Self dot amounts name plus equal amount. So that is how we put the ingredients in there. Reactions equals just a list. All right, so we're going to store the reactions. So, okay, at this point, so a reaction is a pair that has on the left one of these ingredients and on the right one of these ingredients. It just so happens that the one on the right only has one type of ingredient and everything else is 0, but it's still a vector of ingredients. So let's start with the left. So left ingredients equals, so right now they look like that. So it's going to be split on the spaces. Hang on. For token in left ingredients, pair equals split on the spaces. All right, so it's going to be a list which has what? Okay. Okay, left ingredients will be just an empty list. All right, for token, so for each of these tokens, we're going to put a pair which has int followed by the string. Okay, so the split, turn a list, I can't remember. We'll try. So pair 0 equals int of pair 0. So turn that into an int. The other part is a string. So that's the left ingredients. Now make it into an ingredients class. Does this actually work? Looks like it. All right. Right ingredients is pretty straightforward. It's just going to be pair equals right dot split 0 equals... I'm sure there's a better way of doing this. Right, ingredients equals ingredients of just this one thing. Yeah. So we've got left ingredients and we've got right ingredients. So recipe, don't call it recipe, reaction. And just the pair. Left ingredients, right ingredients. That says this vector gets converted to this vector. Okay, that's a start. We print reactions. We're not going to see anything in any of the contents because should we try and make this readable? All right. Define rep turn string of self dot amounts. Try that. Is that not what we want? Or do we want this? How do you... I forget how to make them... Oh, no, it's repper. That's why it was... Okay. That's a start. Can we just... Can we make this a bit more readable? String of... Can we just convert it to a regular dictionary? Then we don't have all this preamble. There we go. Okay. Alright. I'm getting somewhere. What else? All right, so we need some sort of addition, subtraction. So start with addition. So ultimately, maybe this is not, maybe we shouldn't provide shouldn't provide a list like that. That's a bit weird. Instead, provide a dictionary. Because then you can create a copy of ingredients just by supplying amounts back into the constructor. If I want to do that, we would do this. So for amount, so it's going to be for name amount in ingredients dot value dot items self dot amount name plus equal amount. So we have to provide this a dictionary. That's probably cleaned this up a bit. So okay, for token and left. So okay, left ingredients is just going to be this dictionary. Should we even use default dict? Yes, because we want to add things to 0. All right. Wait, why would we be adding? Oh yeah, because we increase ingredients. All right. In fact, you know what? A recipe shouldn't be a pair of things. It should just be a negatives and positives. So you subtract a bunch of things and you add a bunch of things. That's what a reaction is. Okay, well, we can do that. So how do we do that? So for token and left, it's going to be an int followed by a name. Okay. So we don't need to say left ingredients, just say ingredients. So for token and left, pair equals token dot split. So we don't need that. We can just say left ingredients. So the name will be pair 1. And the int will be minus int pair 0. This. And then for the right, we do pair dot split, and then we do the same thing here, but we do the positive. So you subtract a bunch of things, you gain a bunch of things. The things you gain are the things on the right hand of the reaction. So ingredients pair 1. Just to be absolutely safe, we shouldn't put equals here, we should add, because they could have a reaction where you use an ingredient to get the same ingredient, but like let's say you lose 1 ore and then you get 5 ore. Why they would do that, I don't know, but let's cover that case in case. So do that. In that case, this needs to be a default dict. All right, get rid of this. Get rid of that. All right. And by the same reasoning, we should actually just do this. Okay. Reactions, put the ingredients. All right, let's see it now. default dict. Print reactions. Oh, because we haven't made it in ingredients. Let's do it with just a basic dictionary. Okay, there we go. So it's like -3 of that, -3 of that, -1 of that, 2 of that. That is a vector. You can just add that whole vector to your current state and you get the next state. The next state may not be valid if there's any negatives. All right. So we can say define. So in our breadth-first search, we're going to be choosing reactions based on whether we can actually add them or not. So we need a method. Define can add and this is saying if we're going to add this new thing, we need all the amounts whenever we add each of these ingredients, so they may be negative, we need all of them to, we need to leave us, so we should never go below 0 if we try to add these numbers. So we should say return all, so it's going to be other, so other k plus self dot, oh, so it's going to be other dot amounts k plus self dot amounts k is greater or equal to 0. That means for k in other dot amounts. So if we just add each of those other things, it shouldn't put us below 0. So that means we can apply this reaction, but the generic meaning is can add this other vector. Okay. So just define add. So we create a new dictionary, which is like new ingredients equals just default dict, I guess. For kv in self dot amounts, new ingredients k equals v. So make a copy of our amounts. Can we not just say, I don't know if you could do a clean copy. Should we try? Self.amounts.copy. I think so, because these are primitives, strings and ints. For kv in other.amounts, new ingredients, k, let's say v, return a new class based on these new ingredients. Right. Okay. I think we've got the building blocks here. So we're basically trying to count from 1 ore upwards. I mean, out of all of these, all of the ones involving ores, it seems we need at least like 100 or something, but let's say min ore, min starting ore equals minimum of, for the reaction, so it'll be the minimum of all the negative ores. So it'd be like R or if R or is less than 0, that means we're using it. So we actually want the max. That'll get us the smallest amount, just minus that. Oops. For R in reactions. Print start at ore count. All right. Dot mounts or expected else. I thought you could do this. A max of Can I do it like this, when it's a list? Oh, but I think you can if this comes after this. It's a filter. Yeah, you can. Starting at 111, is that right? Yeah. Okay. So we need, okay, we need a let's say DFS because it's like most lightweight. DFS for starting ingredients. So we need a queue, which is just a list with containing start. Visited is just a set of things we've already visited. That means we're going to have to hash ingredients. How do we do this? We're going to have to make a list, a tuple of all, make a list of all the, okay, hang on. Get hashable rep. So we're gonna have to make something which is hashable. So I guess we can just take all the non-zero items, put them in a list and sort it. Yeah, okay. So if b is not equal to 0, then L dot append just k, just the pair, the name and the amount. L dot sort, and then return the tuple version of L, I suppose. So then we can define equality. Be this. And we need hash. This one we just do this. Move this up. Okay, that's everything I can think of. All right, so this is the visited set. We haven't visited anything. While there are elements on the queue, current equals queue.pop. So we have current. The goal is to get fuel to be greater than 0. But we can check that in the neighbors. But right, so for reaction in reactions. So for every possible reaction we can apply. If current dot, so current is a ingredient, so we can say if current dot can add, so we can apply this reaction. Just call it neighbor. It's not strictly a neighbor. The neighbor will be the addition. So current dot can add R. Neighbor equals current plus R. So that's the neighbor. If neighbor dot mounts fuel greater than 0, return true. That means we can find a way to get 1 fuel, at least 1 fuel. You might end up with 2 somehow. Alright, otherwise we just put it on the queue. So, if neighbor in visited, continue. Alright, goal, return false. So our process is or count in count starting from this minimum. Trying, so we'll just trying or count. I'm going to count infinitely upwards. If so the start vector is going to be start equals ingredients. So it's going to be based on the just the dictionary which maps fuel, or to or count. If DFS succeeds on start, break out of this loop. Print min possible. It's going to be whatever or count was left. All right. Now it's the big question. How long does this take to run? At least we'll see the speed of it. I don't think it'll take too long, but I mean, there's a huge breadth. But then a lot of these may not be viable because we don't have the right ingredients. So also I've not tested any of this, so okay, let's just try. KV and other dot amounts. Too many values. Oh, that should be dot items. Okay. Now it's really slowing down. So we're saying if we complete, what is it? What realistically would we expect? Several hundred, I guess, but so this is a binary search thing, which speed this up. This would be good practice of binary search, to be honest. Because I don't practice it much, and I always forget how to do it properly. So should we try that? Let's make sure that it actually can be done for some amount. So let's try 2,000. I assume it can be done for this. Trying or count 2,000. Also, should start. Not that that's really gonna make a difference. I don't know. 1,000. So maybe too many or it just takes too long, but... Are these unique? Oh, fuck. Hang on. There's a way to simplify this massively, but it wasn't clear from the description, but it seems that there's only a unique way to make each one of these. In which case, this is a super general way, but it's not needed. Okay. That means all we have to do really is just take a fuel, look at what makes it, and then expand each of those recursively until we get them all to ores. Yeah, it looks like they are unique. Well, maybe it even said that. Hang on, stop the program. Almost every chemical is produced by exactly one reaction. The only exception, ore, is the raw material input to that and is not just by reaction. Oh my god. We've just gone and programmed this whole complicated thing for no reason. This is not a generalized problem. There's a unique way to make each thing. So it is known. It is a tree problem. Oh, bloody hell. Okay, fine. So the DFS is useless. Let's take that out. The ingredients is overkill, but not useless. We can use that. So, fine, we've got a list of ingredients, whatever. That we probably don't need it. Yeah, this is just a case of expanding the reactions, isn't it? Fuck's sake. And a reaction is always gonna have... Alright, fine, whatever. That will hide our ingredients for now, because we actually don't need it. Alright, reaction. So just hide this for now because probably won't need it for part 2. Unless they do actually generalize. That would be interesting. Okay, so ingredients. Okay. Left. Alright, left, right. Okay, so start here. We've got left and we've got the right. The right. still a bit confusing. But okay. Because the rights, these are amounts, but fine, we can deal with this. Okay, so on the left-hand side, I guess okay, so we want a hash map which maps an ingredient to what things what is composed, what ingredients are used to make that, right? So it's a bit weird because the right-hand side is not always one ingredient. It's usually not. Okay, but anyway, so the product equals equals right dot split dot so yeah, it's the second part of that. Quantity equals right dot split 0 entered. So I guess on the left, replace left with just a list of so left right now is just these strings, so just change them to pairs for like names and amounts. Oh man, how do we... Okay, just store the information to begin with and worry about it later. All right, left equals token dot split 1 token dot split 0 Okay. We just want to say reactions is actually going to be a hash map. And we do reactions for this particular product equals the pair, which is the quantity you need to make, because you can't go lower than that. You actually have to make that amount of quantity in one block. This is really weird then. So need to make that many DBVDs. All right, so this might work. All right, so the quant followed by the amounts of things you need. Okay, so that's stored all the stuff, right? So let's get rid of this. Token.split 1, token.split 0 for token in left. What's left again? Oh, that shouldn't be commented out. Okay, so LQNR, you need to make 2 of it, and you need those things. Okay, got it. All right, so now this is recursion, essentially. Define or needed for a thing so what are we calling these? Metals? Chemicals, I guess. Okay. Chemical and amount. So this is what we need to do. If we need to make this amount of this chemical, we need the amount of ore we need. Minimum amount. Okay. So we look up the recipe for that ore. Okay, so the quant is the amount you would make with one reaction. Quant followed by the ingredients equals, it's going to be reactions for that chemical. So that just looks it up. All right, so num reactions, it's going to be basically the number of quants we can put together to make amount. So it's going to be amount divided by quant ceiling. Like this. To at least make that amount. Okay, so that's the number of times we have to make this reaction. right? So that's bona fide. That many reactions need to be done, and so then we need to find out the ore needed for each of these individual ingredients. So for ingredient num of ing amount in ingredients. So ing amount is how many would be in one reaction. So you have to multiply that by the number of reactions. So result is 0. We're going to have to result plus equal or needed for that ingredient recursively and that ing amount multiplied by the number of reactions we need to do. We return the result. We didn't need the base case, so if chemical is or return amount. Okay. Print or needed fuel 1. Alright, if this is right, that means we basically wasted a lot of time with that BFS, DFS approach. Not correct, it's too high. Minimum amount of ore required to produce exactly 1 fuel. So they... Why, when they say exactly, well, I don't think that matters because we're finding the minimum. Alright, what's the problem then? Okay, we can test it on the examples, but let's go have a quick look at this. So this chemical and this amount. If it's ore, return the amount. Okay. Alright, so quantity and ingredients is just expanding the reactions for that chemical. Num reactions will be the number of times we need to do the reaction until the accumulated quant is at least the amount we're asking for. Yeah. Result is 0. So for each ingredient and the ing amount, we're adding the ore needed for that ingredient, and the num is going to be the number of reactions times by the number you needed for each reaction. So that'll be the total amount, and that requests how much. Oh. No, that's fine. Alright. 2108323. Does that sound too high? Alright, well, we'll try the small examples then. So is this the simpler one? $41, they're saying. What was the oops. Total of 31 ore is required. Why did I get 41? So it's 10 ore to make 10A. So let's print some stuff then. So print so and so chemical needs so and so ore. Let's just see what we're getting here. One fuel needs 41 ore. So we've said 7A needs 10 ore. Ugh. That's not right, is it? 7A. So that many chemicals. So our reaction says 10 ore makes 10A. That's right. You need 10 ore to make 7A. Sure, that's fine. 1B needs 1 ore, correct. 1C needs 11 ore. 10 ore plus 1 ore. 11, correct. 1D needs 21 ore. Oh, I see where we're going here. 1E needs 31 ore. But we have all this leftover A, don't we? We don't really want to waste leftover A, because that could be used for the final reaction. Oh man. All right then. This approach doesn't work as is. What do we do now? If we could do it, we could do it like floating points, but then the problem is... No, that won't work either. We have to do topological ordering. This means we actually could reuse our ingredients class. Probably don't need most of the contents though. So probably don't need that. We don't actually need these yet. That. So basically, we take one fuel, so I reckon what we do is we always take the highest ingredient in the topological order. So ores, A's, and B's, they're at the bottom because they're preceded by other ones which rely on them. So we always take at each step we take the top one and break it down into what is needed to make it. And we keep all the leftovers. If we follow the topological order, I think we won't waste leftovers. Because when we get to the point where A's are needed, we'll have added it to all the A's together. So let's try that. So we don't actually want this method either. Start fresh-ish. All right. So we do actually want ingredients. So let's say ingredients. So as before. So we don't do that, but we do store quant and an ingredients class. So we need this basically. A token and left peg, token dot split, ingredients pair 1. We don't need so many lines. Let's do this. So ingredients is default dict, token in left. We put that with the amounts. Take these. So we don't need the right. Okay. So a reaction for a given product to make a certain quant needs this set of ingredients, okay? And it should be the ingredients class. So A needs 10, A to make 10A you need 10 ore. B to make 1 you need 1 ore, and so on. All right. Fuel 1 and so on. All right, got it. That's our information. All right, now get rid of all this. The DFS definitely isn't needed. All right, so start equals is fuel always 1? Yeah, I guess so. It was in our case. So we start off with reactions for fuel. So that gets us the pair. It's the brackets. Reactions for fuel. 1. That gets the ingredients. So we've got an ingredients list now. We need to make that. So in each step, we pick one of those ingredients which is in the highest of the topological orders. So now we have to make a topological order. Get rid of all this as well. By that I mean just create a dependence. Okay, let's make a. Oh dear. Okay, just dependency equals it's just everything points to the ingredients it needs, so it's gonna be a default dict set for R in reactions. So for each thing we produce for ingredient in reactions are, take the ingredients list for dot keys to dot, hang on, so that's an ingredients dot amount dot keys. So all the things it contains. If v is greater than 0, then dependent c r dot add ingredient. All right, so r points to ing. Okay. Now we want to create a, I can't remember how to do this, a topological sort for this graph. Oh, okay. All right, just copy something from the Geeks for Geeks, I don't know. Topological sort, recursive function. All right, we'll just copy what they've done here because I can't be bothered to write my own. So here we go. Okay, class graph. Change that to a set. We don't need so we don't care about v, do we? Add edge from, so that'll be R2. That'll be reactions. Add v, okay. Recursive function used by topological sort. Okay, just assume that works. Self dot. So this will be just length of self dot. What is it called? The graph. Okay, self dot graph. Number of things. Turn stack. Okay, test this out. So man, I thought topological sort was easier to write. I'm sure there's an easier way. All right. G equals graph. So then we put all the edges in. For RM reactions, blah, 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 blah. Okay, what's dependency? Get rid of dependency now. We got rid of it. Oh. Okay. G dot add edge. So it'll be R and ing are and in. Okay. Print g dot topological sort. All right, let's see if it does what we want it to. Debug, stop. Okay. 543210. But we actually want the. I want the vertices. I want the what's the right? Not visited. Let's sort this out. Visited is a set, not a hash map. It's going to be v to false for v in self dot graph. Right, that's the vertices. All right, stack is that. We don't want this. We want for v in self dot graph. So they've done it in a weird index way. That's not ideal for graphs. If visited, if just why are you doing equals false? Don't do that. Not visited. I b self topological sort. That edge visited stack. Okay, and then return stack. That's sorted. And then here, topological sort. Visited v equals true. All right, fine. For I, so here we want v. Wait, what? Yeah, okay. I in self.graph v. If visited I is if not visited. The I, we call that on I. And then we push that vertex v, but that's a vertex. Okay, okay, this is better now. Try this. Key or visited I. Ah, because or is not, fuck's sake. Okay, visited is default dict Google. It's false by default, right? That should work. Dictionary change size during iteration. For v in self.graph. Well, all right. Wait, so can we refactor that? That looks stupid. Refactor, rename. There, yeah, there we go. All right. This one too. Okay. We just need to know all the nodes, all right? So Every time we add an edge, self.nodes.add u, self.nodes.add b. All right, now we know all the nodes. All right, doesn't need to be the start of an edge. It's either the start or the end. All right, so now for v and self.graph. So what was the problem? V, okay, so for v self.nodes. Okay. For I, okay, try this. So it's saying go in this order: fuel, E, D, C, A, B, O. All right, fine. Now, we start with this reaction. We start with this list here. We're trying to get fuel. So start, print start. Start is A7E1. Okay. So what we're going to do is start with whatever is highest in the topological order. And that's E. According to this order. And that's important because E will be processed before A. So we don't discard A's. If that makes sense. So we want to pick the... Okay, so while there's anything that's not ors, while we still haven't brought it down to the ors. So while any k is not equal to or and v is greater than 0 for kv in start, so don't call it start, call it no current, whatever, current. All right. Current dot amounts dot items. All right, so this keeps going until we're left with only ors. All right, so we have to first choose whatever is an ingredient that's highest in our topological order. So we want to pick the minimum index in this list. So order equals that top order. So min ing equals minimum of current dot amounts dot keys key equals lambda. So we take an ingredient, map it to top order dot the index that it's found in our top order. So that's the minimum ingredient, right? Okay. Now, why are we doing this? Because we need to make that many ingredients. And there will never be more of that ingredients to make based on some other chemicals we broke down. Because this is the top of the topological order. It's the absolute top of the hierarchy. Everything is dependent on this now. So it won't be the case that we find some leftovers that we could have used, as is what happened with the A's. So so this is the amount we need to make. So the quant equals current dot amounts dot wait, what? Minting. All right. So we need to make this ingredient and this amount. Okay. So we look at the reactions. So the product and ingredients equals reactions of this minting. So this tells the formula how many we need, how many will be produced, and what ingredients will be used to produce it. Oh, I just realized we need another method in our ingredients. We need scalar multiplying, don't we? So num reactions equals so we need to make quant. So we need to count how many of these products. So it's going to be quant divided by product. Seal. Round up. Is there a... What does round do? Well, it rounds down. Alright, we'll just stick with seal. Num reactions is that many. So we need to do that many reactions. So we need to replace current. Hang on. So new ingredients equals current dot amounts dot copy. So we take what we currently have. We've satisfied this particular product, the minting. So we remove that. So you delete new ingredients in ink, and then we have to add the reactions. Oh, okay, well, either we make a scalar method, and we probably should, so it'll look like this. We want to say current or we can call this delta ingredients equals just minting minus quant. So adding that will cancel out what we currently have. Right. Or product. A V in ingredients dot amounts to items. So for each of these, we're gonna have to add in this to the delta. So delta ingredients for that ingredient plus equal, it's going to be V times num reactions. And finally, current is actually just going to sum with delta ingredients. Just keep doing that. And then finally print current. Oh my god, this actually works. Key error A. V times num reactions. Delta ingredients K. It's gonna have to be default text. But why? Yeah, okay. Always use the default dict in this case. No attribute amounts. What? Add KB. Oh, current plus equal ingredients. We've got to make that into a class before we can do that. A7E1. Stuck in a loop. So while there is any K not equal to or, and what's going on? So it's stuck here. So it's trying to do this. So it's broken down to this. That looks alright, I guess. Oh, because we're choosing E, but E is 0. So it's the minimum of current.amounts.keys. So it's got to be K for current, K in current. If current.amounts K is greater than 0. Only positive ones. All right. Or 31. Print current and just get the actual final answer. That's correct for that test example. Print current dot amounts, or there we go. Bloody hell. Now, will it work? Shouldn't take long now because it's breaking down one thing every time, so it should be completely linear. Not completely linear, quadratic probably. But there we go. So it's less than what we had before. Oh, that was part 1. Oh man. After collecting ore for a while, you check your cargo hold. 1 trillion ore. With that much ore, given the examples above, given 1 trillion ore, what is the maximum amount of fuel you can produce? Oh, bollocks. You can't do this in reverse because you have the leftovers. We make this a fractional thing. Hello, DJ. How goes the programming? It's gone okay. 13 was an easy day. 14 is quite tricky. Part 1 was quite tricky. Seems like we've got a bunch of chemical formulae, and we need to choose the combination of those chemical formulae to apply until we get 1 unit of fuel. Each formula is like a bunch of ingredients added together will make a bunch of will make some element. So now the question is, we have 1 trillion ore, which is the most primitive ingredient everything gets made from. And we want to see how much fuel we can make out of that. It seems like there's an easy way to do this then, because I think, so using what we did before, we found that 1 fuel uses X amount of ore. But you can't just divide by X because it's that includes wasted ore. Wait, how does this work? So if we want 1A, we can use this formula here, but this gives 2A, and we're not allowed to halve it. So if we want 1A, we need 9 ore, that will produce 1A, and then we get 1 additional A. So either we go into fractions, we say if we want 1A, we need 4.5 ore. Or we say so why wouldn't that work? Maybe it will. We just turn everything to fractions. So it's as if so in this example, 1 fuel needs these. So to make 1E, we would need these, and so on. When we get to 7A, we want 10A. So instead of 10A, we only want 7A. So we'll say we'll take 7/10. So we'll take 7/10 of this, which is 7 ore. Now, no, that's not quite what we want though. Even 1 trillion ore, what is the maximum amount of fuel you can produce? Well, let's turn this around. Let's say if we wanted to make 100 fuel, we already know how to find what we need because we already have this method. So let's just test that out. So we simply do current equals reactions. In fact, we shouldn't have this. What we should have is just this. Ingredients. Fuel 1. Like that. So we should get the same answer. 1920. Yeah, okay. And don't print stuff. So actually, is it not as simple as just changing this to be a large number? And it should take the same amount of time. And then we just have to find the number which is under 1 trillion. Okay, so let's try this. So that's part 1. Part 2. Right, stop printing stuff. Current equals, so we have to do all of this again. All right, wrap it up as a method then. Define get min or to make a certain recipe, to make ingredients. Just do that. Return current dot amounts for. So we print. So for part 1, print get min or. It's gonna be like this. For this. Alright, check that we get the same answer now. Okay. Part 2. Just take this, change this to 1,000, let's say. So to make 1,000, we would need this. 1,000 million, almost a billion. So add another 10. I'm doing binary search by hand. 1,000 millions, billions. So we want to find the number. Minimum amount of ore required to produce exactly 1 fuel. We shouldn't do binary search. We should Okay, let's wait, there's a module in Python for this. Should we try it? Bisect. Python bisect. Array bisection. But I don't. No, but it uses lists. All right, just write binary search from scratch. Good practice. All right, let's see. Min equals 1, let's say. Max equals... Hang on, so we're trying to find the minimum amount of ore. So we're trying to find the maximum amount of fuel you can produce with a trillion. We're trying to maximize a value x, which is the amount of fuel, such that running this method will be under... Okay, so ore cap equals 1 trillion. So it's 1, 2, 3, 3, 2, 3, 1, 2, 3. It's thousands, millions, billions, 1 trillion. Okay. Okay, so we know that a minimum viable, so left equals 1. All right, we know that we can make 1 fuel with this ore cap. Or should we just be super general? 0. No, 1. Okay. Right. Equals, well... We know that we would need... Can we programmatically find an upper bound? It's something that we can't make. Do we know for sure that we couldn't make that much fuel with that much ore? Kind of, because... Okay, we'll just use that as the upper bound. Okay, so we know we can't make that much. We can make that much. We can't make that much. We're trying to maximize... we're going to keep changing left and right until left is sitting on the maximum amount we can make. Okay, so while left is less than... While, let's say, while right minus left is greater than 1. As long as there's still a gap between them, we can close the gap. So we want left and right. We want right to be left plus 1. Then we've squeezed the gap, and left we can do, right we can't do. So we found the max. So while right minus left is greater than 1, we want it to eventually be equal to 1, okay? Mid equals left plus right over 2. If get min ore for that amount, that much fuel, is less than or equal to ore cap, we can make this amount, therefore left equals mid. Else, we can't make this amount, therefore right equals mid. So that will halve the gap each time, and then we just print left. All right, let's try this then. One 1330066. I mean, we can actually try this by hand. Correct. Binary search. Can't remember the last time I wrote binary search. I'm surprised there's no binary search module in Python. That just to replicate what I did there, but I hate having to think about left and right and mids and indices and stuff. You would think you could just have a function which says, like, maximize this function with these bounds and then just do it. But I'm always having to write that mid, left, right process every time. Whatever. Okay, that was a good problem. I went down a lot of wrong avenues there. That took me about 2 hours. Yeah, it did. It took me 2 hours, over 2 hours, just over. Yeah, because I did go down some wrong paths. Topological ordering is important. This stuff isn't needed anymore. Take that out. Yeah, we didn't need that either. Okay, I'm not sure how you would do it without topological sort. You just got to, I don't know. I suppose there's some randomizer methods for. I mean, topological sort is not hard to program. It's just I was too lazy to do it. I mean, you do that. You choose every time you choose the edge, which is something, and then you get something. All right. I think that's enough for the day. 2 problems. That took me enough time. But we are over halfway now. But are we really? We should take a sneak peek at 15. I think halfway point is probably, in terms of amount of work, it's probably around 19 or something. Take a sneak peek. Is it blah, blah, blah? Of course it's ink code. But I feel like the fact that we built this complex ink code makes these problems easier, because part of solving it involves making encode in the first place, but we've done that already, so I feel like it may be easier. I don't know. It looks like a BFS problem. Minimum path, something or other. Minimum, fewest number of movement commands. Okay. Fine. But this encode stuff was a very cleverly designed thing, like... And we're no longer having to do assembly, because we've built the encode. Now we're just doing interesting things with it, and making minor changes to it, which don't actually involve looking at the assembly anymore. Alright. So that's... Oh, we're catching up to Pararonia. We just need 3 more stars to overtake. And then let's have a look at 21's leaderboard. Oh, okay, lots of people did those, so I would have a long way to go to overtake there. Cool. Alright. I can't really tell whether that 14 was hard or easy. It's difficult to judge. I mean, topological sort is not hard, but it's also quite academic. Like, you don't really come up with it from first principles. Well, actually you can. But it just takes a bit of insight. But once you know it, you can just copy and paste the thing in like I did. Yeah, overall this is quite a clever problem. Alright. That's it for today. See you next time for more Advent of Code starting from day 15. Bye-bye.